We've all been there. You're working, clicking, typing, and suddenly the mouse pointer just stops. The screen ignores your keyboard. Your expensive machine has turned into a very expensive brick. Under the hood, this freeze is usually caused by a deadlock. It happens when multiple internal processes try to grab the exact same limited memory or processing power at the exact same time. Look at this logic board to see what an unsafe state looks like mathematically. We have exactly one resource available, but three active processes, P1, P2, and P3, are demanding 3, 2, and 4 resources respectively. Every single process needs more than the system can currently give it. Because no process has what it needs to finish its task, none of them will let go of what they already hold. They will wait forever. To prevent this trap before it springs, operating systems use a predictive diagnostic tool called the banker's algorithm. It acts like a highly rigorous traffic controller for your computer's resources. Keeping a system running smoothly isn't solved by simply cramming in more hardware. It requires the software to look into the future and calculate a perfectly safe order of operations. Let's run a simulation of a healthy system to see how this works. We have 3 active programs running, drawing from a central pool of exactly 3 available resources. This table displays our current board state. Each process already holds 1 allocated resource, but to finish their jobs, they have maximum limits they will eventually hit: 3 for P1, 2 for P2, and 4 for P3. To figure out exactly what's required next, we create a need matrix. The formula is straightforward. We find the need by subtracting the current allocation from the max. For P1, a maximum of 3 minus an allocation of 1 means it needs 2 more resources. Applying that same logic populates the rest of our board. P2 needs 1 more resource, and P3 needs 3. The algorithm operates on one strict conditional rule. A process can only run if its specific need is less than or equal to the total available resources. Looking at our options, P2 only needs 1 resource. Since we have 3 available, we can safely clear P2 first. P2 takes the resource, executes its code, and finishes. Crucially, it then surrenders its previously allocated resource back to the main pool. Our available total flips up to 4. By identifying and feeding the least demanding process first, the system recovers held memory. The central pool actually grows, giving the computer the capacity to tackle heavier tasks next. With P2 out of the way and a newly expanded pool of resources, we reevaluate the board. Our available counter stands at 4. P1 needs 2 and P3 needs 3. Both remaining processes theoretically fit within our new limit. We'll queue up P1 to run next. It takes its 2 resources and gets to work. Once P1 finishes executing, it drops off the board and releases its allocated resource, which pushes our total available pool to 5. You can see the momentum building. Every time a program successfully finishes its loop, the resource pool grows larger. We are down to our final, heaviest process. P3's demand of 3 resources is easily handled by the 5 we now have on hand. P3 executes. P3 completes its job, hands back its allocation, and our available counter hits a final total of 6. The board is entirely clear. The chronological path we just traveled, P2, then P1, then P3, is officially known as a safe sequence. Calculating this specific procedural sequence is the only way the computer can mathematically guarantee all programs will finish without gridlock. A system operates in a safe state, as long as the algorithm can map out at least one of these safe sequences. If that safe state is confirmed, a deadlock is mathematically impossible. Resource requests are granted, and the system continues to run. Conversely, if the algorithm runs its checks and cannot find a sequence, like that initial scenario where demands outmatched the resources, it simply refuses to grant the requests. It denies the action to prevent a crash. As a user, you never see these matrices or calculations. What you experience is simply a fast machine that opens your apps, renders your videos, and browses the web. Millions of times a second, this invisible data is routed smoothly and rapidly through complex pathways, perfectly dodging any potential collisions. This continuous, invisible arithmetic, constantly predicting the safest path forward, is the hidden foundation preventing our complex digital world from grinding to a halt.